Hello everyone, this is RaySpace, here to discuss the design of the ultimate spaceplane. Well, you'll get to decide whether it's the ultimate spaceplane or not. I'll describe it and tell you why I think it is, and you will get to decide whether I'm right or wrong. But it has featured recently in my Project Starlight videos. I sent it to a landing on the moon and brought it back. It did need some refueling along the way, but it is functionally a single stage to orbit, though as you can see it launches on a rocket sled initially, and that's because it's really hard to get it off of a runway given how heavy it is. It does not have a thrust-to-weight ratio of 1. Even with its rocket engines ignited, it does not initially have a thrust-weight ratio of 1. It does have a better thrust-weight ratio once it gets higher up, but it really can't lift off vertically at all. It does have ramjet engines. Those are actually the most technologically difficult part of this, believe it or not. The rest of it is actually pretty easy to deal with. Getting the ramjets to be the mass that they currently are, they're 3.5 tons apiece, generating 1,350 kilonewtons, is actually pretty darn hard. And if I could remove them entirely, I probably would. But right now, we can't do that. Now, this design originally started out as the Scramspike, or Scramspike, and the idea was to make a single stage to orbit spaceplane that had a scramjet at the bottom, and that got it to Mach 10 or possibly up to Mach 12, depending on exactly the configuration. And then the aerospikes in the back would boost it further along all the way to orbit. The reason that I had thought of this is it turns out that the curve that the scramjets normally need in order, they basically have a really big nozzle at the back, but the curve of that effective nozzle surface matches the curve of an aerospike, and so I decided, well, we might as well just have an aerospike there too. But now I have removed the scramjet. We no longer have a scramjet there, and that's because I wanted to instead install something that would allow this more flexibility when it goes to other places. So it has landing engines. Those would not be able to land on Earth, but it can land on other bodies. And it also has in situ resource utilization, that is, the ability to drill for especially water on other surfaces. It has an air intake, and that air intake can take in carbon dioxide or methane, and it can combine those into methane, hydrogen, and oxygen. Really, it'd be splitting the water into hydrogen and oxygen. In order to split the water or to do this conversion, it needs power, and that is one reason why we have a reactor. Actually, this was supposed to be the reactor, but I found out that doesn't work quite as well with KSP Interstellar, so I decided to just use KSP Interstellar's molten salt reactor and thermal power generator, which were actually the same size anyway. And so we have two of those, one on each side, and then we have the drills and the landing engines. So, the landing engines, each of these nozzles, I actually thought there were 24, but there are actually 20. I mistook at some point that there were 24 of them, but I only put 20 of them. But they're 48 kilonewtons apiece. They can land on the moon. They can't land vertically on Mars. So on Mars, we will need some sort of flat surf runway or something to land on, but it can. They'll still be firing in order to make it easier for us to land on such a surface, but we'll probably need some runway for that, and also for takeoff. They'll help with takeoff, but mainly we'll be using the aerospike to boost us up. The aerospikes, there are two of them, produce 2,000 kilonewtons each. However, that's when they're burning 3 propellants. So this is filled with 3 propellants: liquid methane, liquid hydrogen, and liquid oxygen. And the landing engines use hydrogen and oxygen, and they get 400 seconds of ISP, which is not much for a Hydrolox engine. These on the tail, though, these aerospike rocket engines, they get 450 seconds of ISP with the Hydrolox because they have a lot of chamber pressure, but they only get their full thrust with the 3 propellant mix: methane, hydrogen, and oxygen. And right now the configuration is a little bit wrong, but I'm going to fix that. But they have three configurations: a Methalox one, a Triprop one, and a Hydrolox. And ultimately the Hydrolox, I changed my mind basically about this. Initially they were going to have all three propellants flowing through each of these nozzles that are on this Aerospike. Instead, I've decided to change that so that this nozzle, this nozzle, this nozzle, and this nozzle, and their symmetric partners will only have hydrogen and oxygen, whereas this nozzle, and this nozzle will only have methane and oxygen. That'll simplify the design of the chambers because then we don't need to have different mixes going through each chamber. In other words, each of these chambers doesn't have to be optimized for both Methalox and Hydrolox. Instead, there's got to be dedicated Hydrolox chambers and dedicated Methalox chambers. And when we want to burn all three propellants, we'll just be firing all 14 chambers on each of these engines. But when we only want to do Hydrolox, we'll burn the 8 chambers that do Hydrolox. And we only want Methalox, we'll only use the 6 chambers that do Methalox. And so, in theory, that would simplify the design of the Aerospike, but it's still really, really complicated. The reason for this is because we get different propellants in different places. We can get water most places, really, but it's beneficial to have methane. One reason I wanted to add methane into the mix instead of just doing hydrogen and oxygen, which would be much simpler, is because methane is more dense than hydrogen. And by giving this 3-propellant mix, it allowed room for a cargo bay. And so we have a cargo bay here, and that cargo bay adds a supplementary area or volume for radiator panels. I've added radiators to the upper body of this. That's what those stripes are. And really, it probably should have them on the upper side of the wings as well. But we are going to probably need more radiators here because, again, we have nuclear reactors. Now, we need the nuclear reactors not only for the drilling units, but also because this features ion engines. Actually, pulsed inductive thrusters apparently are the things to go for. They're a type of ion engine that works a little bit better with oxygen and scales a little bit better for this kind of power. Pulsed inductive thrusters, unlike ion thrusters, don't just physically scale up when you put more power into them. Instead, what they do is they increase the rate of the pulses. So they actually pulse out the propellant. And so if you put more power into it, you just increase the rate of the pulse and get more thrust. So that way it scales a little bit better. And here we have 2 units, each with 10 thrusters. They weigh in at 2.27 tons apiece. We'll go through the whole mass of all of this later. But they use oxygen because I didn't want to carry xenon gas, which wouldn't be used for anything else. This way, when we replenish, we can replenish the oxygen as well, once again from the water, and use the oxygen in order to have ion efficiency, even though that's really slow, 2,268 seconds of ISP. So that's sort of the fancy feature of this. Initially, the Scramjet Aerospike had 3 Aerospike engines at the back. I removed one of the Aerospike engines to allow for the ion engine units. That way we keep the whole thing a little bit balanced. Though they are actually heavier than one of the Aerospikes, but that's fine. We are now going to be putting a radiator in here, which happens to be about a ton, and so we'll keep it balanced. The ramjet engines here actually use the methane. So they'll be burning the methane first. What will happen when we go to orbit is we burn the methane to about, well, between here and here. And then we go into tripropellant mode. So it'll burn the methane, oxygen, and hydrogen. And then it'll go into hydrolox mode and then burn the rest, is how it all goes. And it'll get less thrust once it's in hydrolox mode, but by that time we'll be so much lighter it'll be okay. Now with the ramjet engines, actually I should have retained the air intake for the scramjet down here. And that's because they were always meant to have more intake area than what we see at the top here. In fact, in a lot of angles of attack, these intakes won't be getting much intake air at all. So they really need the intake at the bottom also bleeding into them in order to run it. The turbojet ramjets probably should have a high bypass thing because of the efficiency I'm expecting from them. And whether you can make them each be 3.5 tons, considering the thrust that they have, that's the toughest part of all this, actually. So if I could remove those, I would. Now, this whole business is not really meant to be a cargo vessel. It's just meant for crew. And so it's more of a luxury liner or emergency vessel or something like that. And the fact that we now have a cargo bay allows maybe us to put in some cargo once it makes orbit around Earth, but it wouldn't be able to carry that cargo up with it because it's so delta V constrained since it's an SSTO. And it's got so many other things that's carrying this ISRU unit, the landing engines, and all that. In fact, let's take a look quickly at the whole mass breakdown. So, this is how it all actually ends up. We've got the jet ramjets. They're the heaviest propulsion element. Right now, using methane, not kerosene. Keep that in mind when you're thinking about the efficiencies. 7,000 seconds in jet mode. That's why it probably needs to be a higher bypass than I've designed it to be. And 3,600 seconds ramjet. Now, if we can get to a higher altitude more efficiently than I normally do, then it'll probably be better off. The efficiency is a direct result of how well I fly it up to, say, 22,000 meters. If I could fly it a little bit more efficiently, break the sound barrier more efficiently and stuff like that, then we don't need so much efficiency. So we can work on that. That's what it needs right now, let's say. It's got two of them. They're 3.5 tons apiece, and so that's 7 tons of those. The Aerospikes get 355 seconds in Methalox mode, 455 seconds in Hydrolox mode, 2,000 kilonewtons when all three propellants are being used. They're 2.5 tons apiece for 5 tons. I mean, this is just a round number, obviously. The rounder the number is, the more it's just me guessing what it might be. The Hydrolox landing engines, we've got 20 of those. I, for some reason, at one point thought it was 24, but we've got 20 of those. The mass of them is 96 kilograms apiece, and that's 1.92 tons. The oxygen pulse inductive thruster units have practically no thrust. That's their efficiency, and they're 4.54 tons altogether. We've got 2 tons for our Sabatier process ISRU unit, 1 ton for the electrolysis portion, and 675 kilograms for the drills. The canards, the wings, the vertical stabilizers, body flaps are all massed by FAR. I don't set those masses. So FAR took the area of those things and decided that that's the mass you need to have them be Spaceplane compatible. So I'm not doing anything with those. Those are the masses. It should be noted that the wings are about the same mass as the space shuttle's wings, and that seems about right to me. Landing wise, it lands at about the same speed as the shuttle while having about the same mass as the space shuttle dry, and so that all jives with what I would expect. Going up, it is much heavier than the space shuttle because the space shuttle doesn't use wings going up anyway, but it needs a lot more speed, so it's all right. So we've got that. The landing gear, because I tweak scaled adjustable landing gear in the game, it's 6.09 tons, which is really high. The actual mass of the space shuttle landing gear, and since we're the same mass and landing at about the same speeds, we should have about the same landing gear mass, was 2.61 tons. So I've just written that in, and instead of, since we've already got this mass attributed to the landing gear in the game, I've sort of shifted the pressurized cabin mass and the instrumentation and seat mass here to just make up the, just compensate for that. So yeah, attributed to landing gear and KSP for the pressurized cabin and instrumentation and seats. That's about 3 tons. Okay, so these are sort of fixed things, and then the rest is structure, basically. So we've got bulkheads, we've got frames, we've got the tanks, and all of this has to be made out of titanium. All of it. Except for the pressurized cabin, which is aluminum. Can you do aluminum? Only if you make it really thin. And I don't know if you can make it really thin. Right now, the thickness of the titanium is 1 millimeter. And the reason for that is the maximum thickness of the skin on the SR-71 as well. The SR-71 had a thickness of 0.5 millimeter to 1 millimeter on its skin. I decided that that sounded good. We still have tiles. Okay, we still have other stuff to keep the airframe cool and everything. So 1 millimeter basically is all the way. If they did it with SR-71, that's good enough for me. So we're going with 1 millimeter thickness. That's the density of titanium there, or this variant of titanium that has aluminum and vanadium in. And so how did I get the surface area number? So for those who don't know, these parts are made by me, and they're not released yet. Maybe eventually they will be released, but they are made by me in Blender, and I make constant changes to them. But the way I figure out the surface area is really neat. In Blender, there's a 3D print module, and you just click area, and it gives you the surface area of that bit. So this is the bottom tiles. This is the upper portion of the body here. I just get the area. There's the cargo bay doors. I get the area. Now, for the doors, it's going to measure the area. And actually, they're not opening. It's going to measure the area on both the top and the bottom. So keep that in mind. So it gets the inner bits. But I can just go around and get the areas like that. And that's how I get the areas for that spreadsheet. And that is really nifty. Now, there's also the internal structure though, right? This is only the exterior of the body. So here we see the general internal layout of the thing. I'm working on the stringers still, so we'll get that measured up. But the stringers go through all the frames. The stringers I don't expect to be very high mass anyway. So mainly we've got the frames and the bulkheads. Those are the things that are really heavy. And this is how it looks. So there's the front end. This is where the cockpit is. This is the rest of the habitat area with the airlock on, well, the docking port on top. And this is the cargo bay area. And then we have our tanks. And of course, the wings have already been masked by FAR, so I'm not doing the frame estimation on that. So we have the methane tank in the middle, 2 hydrogen tanks, and the oxygen tank at the bottom. This ensures that as the tanks drain, the center of mass stays roughly the same, because the center of mass is right here-ish. Liquid oxygen tank might need to be a little bit further forward, actually. But anyway, in principle, it's going to stay roughly the same. It's not going to move around too much. And yeah, that's how we've got all set up. And the tanks are separately masked. So we're not assuming that the mass of the tanks, we're not assuming that the outer structure is the tanks at all. The tanks are their own thing. That way they can have the multi-layer insulation on them to keep them cool, so we don't have so much boil off. So they have their own mass, and they're still titanium. That's hard. It makes this very expensive. This is a very expensive space plane. So when we take a look, we've got those tanks separate here. Those are their surface area and the upper body skin. That, I assume there's no other insulation on top of it. Titanium is really good at heat tolerance and is denser, not denser, is lighter, it's less dense than steel. So it basically does steelish things without being steel. And the rough side is it's really expensive and really hard to deal with. So, but for this, because it's such a specific, it's the ultimate space plane, okay? So we're going to spend money on it. And we'll deal with the fact that titanium is really hard to manage. But that, so the upper body skin on that is about 5 tons there, and we go through. The tiles are separately masked. You can see these are identical because that's the skin underneath the tiles. And we're using the mass estimation for the tiles is the same as the Space Shuttle's HRSI tiles. In theory, the Venture Star Inconal tiles are actually lighter. Inconal tiles improve the reusability. They still have the foam underneath. They've got insulation underneath them. The idea is that the Inconal will stop them from being damaged. So basically you've got insulation underneath, but instead of just being foam, you got a layer of Inconal. Somehow this ends up being lighter anyway because, or Inconal, ends up being lighter anyway because I guess you have less foam. I don't know. Or it's a really thin layer of Inconal. But I read the paper. It basically said it's roughly the same or a little bit less mass. So I'll accept that. If worst comes to worst, we just put HRSI tiles on it. The Spaceplane currently has the same heat tolerance that I had put on the Space Shuttle when I did my early Space Shuttle stuff before I started using the Giulio Dondi Space Shuttle stuff. And that basically allowed the Space Shuttle to barely survive. So I'm fairly confident we are not putting too much heat tolerance on this. This is a barely survivable thing for the Space Shuttle, and that's the heat tolerance I've given this as well. So when it came back from the moon in the previous video, I had to be very careful that we weren't going too low into the atmosphere to air brake, and that's why we needed 2 passes before we got to low Earth orbit. But 2 passes was good enough because it got us to the point where we didn't have to go through the radiation belts too much, but it did require us to do a retro burn before hitting the atmosphere. So we used about 1,500 meters per second to slow down first. Anyway, so we've got those regular tiles, basically, from the Space Shuttle. And then the skin, and then the ISR unit has an inner wall and the door on it, and the door has tiles. And then we've got the cargo doors on top. There's an upper radiator that is a separate sort of unit. It's still titanium. Radiators probably would be pretty good being titanium anyway. And then the cabin. And then instrumentation and seats, 500 kilograms. So not much instrumentation, but we're in the era of touchscreens and whatever, so that's how it's going to be. So altogether, this ends up being 81.5 tons. That's actually a little bit more. I did all this calculation after the fact. I did a rough estimation for the things that I've already done, and then now I've calculated it, and it turns out that it's a little bit heavier than I wanted it to be. But I'll adjust that in the game, and I'll make sure that we can get to orbit with that and do all the things. It's got a lot of delta V. If we go back to the game, so right now it's saying 79.5 tons. That's probably including some food, water, and oxygen, incidentally. So we're a little bit lighter than it ought to be. This is not the real delta V. That's because we've got ion engines, and ion engines always throw things off. But keep in mind, it can land on the moon. It can probably do a decent landing on Mars, and it can land on Titan. In fact, I've already tested the Titan landing and ascent. There are videos on that. So it can deal with the toughest moon of the solar system. Well, no, I guess, well, yeah, but no, it depends on how you look at it. The toughest moon to ascend from in the solar system. And in Hydrolox mode alone, it can get quite a lot of delta V. So let me see if I can show that. And of course it must do, because it has to get to orbit around Earth. The jets don't give you that much. And that's a point. Do I really want the 7 tons of jet and fuel that's needed to propel the thing in jet mode, or can we just use rocket mode and save that? I'll think about that seriously. There aren't too many other uses of the jets in the solar system. So anyway, we're 547 tons right now, so that's why we need the rocket sled. And once we're in Hydrolox only mode, let me just cut the methane and the spare oxygen that we would use in methane mode. You can see that just Hydrolox, we have 6,700 meters per second, and we are 362 tons. So if it's fully fueled, It nearly gets a thrust weight ratio of 1 in the pure hydrolox mode. And actually, maybe I need all the thrust on this then. I'll have to think about that nozzle arrangement that I was thinking of. Maybe I can't do that. So let's take that back for a sec. We might not be able to get away with the fancy nozzle arrangement on these that I thought I could, because I'm looking at that and I'm going, that doesn't look like it's enough thrust weight ratio. Well, yeah, let's set that aside for now. 6,719, that means that if it's just like this, it's got that much to get off the moon. It can certainly land and get off the moon. It's got that much if it replenishes its supplies on Titan. Actually, landing on Titan doesn't take much delta V because it just flies down. So that'll be enough for Titan for sure. We've already tested that. It's just very versatile. It can handle basically any moon in the solar system. The only place it really can't handle is Venus. Of course, no Jupiter, Saturn, Uranus, Neptune, those are gas giants. The downside is it will need a mothership if it's going to go to really far-flung places, because it doesn't have that much space inside. So if you're going to go to like Jupiter, you're going to need a mothership so that it can have the food, water, and oxygen and living space for people on such a long trip. So it can't do that independently. But then after it gets there, it can land. Now you're going, but you're taking these jet engines and wings all the way. Yes, but it can do it. That's the nice thing. It can actually do that. So, you know, we can actually go to the moon with this, land on the surface, and come back, and it can actually do that. It even needs fewer refueling than Starship. So, probably we'd be better off if it's just like this. We certainly cut down on a lot of dry mass. But now it's even more of a platypus. And did we really get that much delta V? When you think about it? We got like 1,000 more. And we're substantially less cooler. We can take off the body flaps as well. So we got 1,000 meters per second, which really in most places we don't need. But we could carry more cargo down like that. And we're much less cooler. So I just decided to keep the wings and the engines and such and be cool. And keep in mind, when we're talking about that delta V, that's just in hydrolox mode with these aerospikes. When you consider how much delta V it could have just using the ion engines, it can do quite a lot with just the ion engines. And again, that just uses the oxygen in here, of which we have a surplus, right? We can see that because the aerospikes don't use all of it, the ion engines get a lot of delta V. If we reverse that, but the ions will use all of the oxygen, and so we can't see how much will be left for the... Oh, well, okay. It's a lot. I mean, this can really power its way through things in systems like the Jupiter system and Saturn system. In the Jupiter system, there's a lot of radiation, so we're mainly talking about the Saturn system. But it can get from one place to another with a lot of ease, from Iapetus to Titan or to stations in between or stuff like that. It's got the delta V to get around. It's also got the delta V to get around like the Mars system, going to Phobos and Deimos and then back. It's got the landing thrusters and all that business. And so, yeah, it's a very versatile spaceplane, considering that spaceplanes already have it rough in Real Solar System and Realism Overhaul. It's very versatile, and it's still within the numbers broadly. The dodgiest thing is actually the jet engines. So otherwise, I've tried my best to make it as legit as possible, as usual, and there you have it. That is the design of the Asuka spaceplane in Kerbal Space Program, and a white paper will be forthcoming. So with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below, and I'll see you next time.